Does printing with a larger nozzle increase the strength of 3D prints? This and the question how you can get the same effect with your standard sized nozzle is what I investigated for this video. Let's find out more. Guten Tag everybody, I'm Stefan and welcome to CNC Kitchen. I'm sure you've all heard or even experienced it already that using a larger nozzle in your 3D printer seems to result in quite a bit more sturdy parts. I also had the same impression in the past, but always ask myself if my 3D prints are really stronger because the layer bond together better, or if it's the additional material you put down that reinforce the parts. So, first things first, let me know in the comments if you regularly use bigger size nozzles and for which purpose. In order to provide you with a proper answer, I've investigated exactly that. For this reason, I printed my test hook in its standing orientation with a standard 0.4 and a 0.8mm nozzle on my original Prusa i3 Mark III's. I chose this combination of diameters because it gives me the possibility to keep the wall thickness the same for both parts. If you've already watched my previous video, you will know that by adjusting the extrusion multiplier, you can not only fuse the layers at least a little bit better together, but also extrude quite a bit wider than the bore diameter of the tip. This also posed the question if, instead of switching the nozzle, you could also use this setting to get the same effect. In the end, I wanted to find out if parts printed with a bigger nozzle are stronger due to the additional amount of material, or if somehow the layers bond together better. As a bonus, I also tried if you can avoid switching nozzles by just using higher extrusion widths. This is the test matrix I came up with. I printed parts with the 0.4mm nozzle using a standard extrusion width of 105%, but we'll also emulate the 0.8mm nozzle by using an extrusion width of 210%, which is pushing material out of the nozzle quite a bit wider than the orifice. For the 0.8mm nozzle, I printed parts with 1 and 2 perimeters, which results in the same wall thickness as with the smaller nozzle, and 2 or 4 perimeters. For one set of samples, I also increased the layer height to 0.3mm, which is more reasonable than 0.15mm on such a big nozzle. As I've shown in the past, layers that are too thin can result in worse print quality. For each set of parameters, I printed 3 samples to at least have some statistics. For these tests, I also used no infill whatsoever, because I noticed that depending on the position of the part on the building platform and the infill algorithm in Prusa Slicer, that the infill significantly reinforces the shell, which will spoil our results and introduce more scatter. I also didn't use layer adhesion samples, even they probably would be more scientific due to the poor tension they are loaded with. They are a bit hard to tune in, but the results correlate very well with the hooks, which are just nicer to look at. All parts were printed in Spoolworks PLA, and I limited the material flow to a maximum of 3 cubic millimeters per second, which is only a fourth or a fifth what a normal V6 hot end is able to handle. This way, we don't get different results due to insufficient melting. All parts printed without a problem. The only thing that I was able to see was that the quality of the hooks with a large 0.8mm nozzle at a layer height of 0.15mm didn't look particularly well. This corresponds very well to my previous findings that you shouldn't go below 1/4 of the nozzle diameter and layer height without extensive tuning. Interestingly, the parts where I emulated a bigger nozzle by upping the extrusion width did basically look the same. When I increased the layer height to 0.3mm, the print results were gorgeous again with the big nozzle. Interestingly, the hooks printed with the 0.4mm nozzle at 210% extrusion width did look differently on the top surfaces. It looked like they were a bit under extruded, but due to the small material flow and also the very similar weight, that's probably not the case. What that basically means is that you can emulate a bigger nozzle by upping the extrusion width, but at some point the flow dynamics under the nozzle will change. For a reference of how far the standing hooks are away from the optimal lying printing orientation, I printed flat hooks with a 0.84mm and a 1.68mm wall thickness, which is equivalent to 2 and 4 perimeters with a 0.4mm nozzle, or 1 and 2 walls with a 0.8mm nozzle. Since you can't always trust the weight values in your slicer, I also put all the parts on a scale to see how heavy they really are. The parts with similar wall thickness weighed pretty much the same, only the hooks from the lying printing orientation differed a bit, probably due to the slicing algorithm. I'll take these values into consideration later when we evaluate the strength by weight. Let's now finally get to the mechanical test that I performed on my DIY universal test machine. Before that, please make sure that if you like this video, you are subscribed and have selected the notification bell. Also hit the like button so YouTube will recommend this video to more science and 3D printing interested viewers. I mounted all of the parts on my DIY universal test machine and loaded them at the same speed to remove the human factor from testing. The load is constantly measured during the test so that in the end I can easily determine the failure load. The 23 samples that I tested failed from 116 newtons all the way to 808 newtons of force. The weakest one was the hook with a small nozzle and only 2 perimeters. The highest strength came from the reference hook that had 1.68mm wall thickness and was printed lying. Since my suspicion was that the higher strength of prints with a bigger nozzle result from the additional material, so in my case, thicker walls, I grouped the strength values for wall thicknesses. The results for the parts with 0.84mm walls already confirmed this because the average strength of the parts is almost exactly the same, though there is more scatter at the parts printed with a 0.4mm nozzle as with the parts printed using a 0.8mm nozzle and just 1 perimeter. The reference hook in the optimal printing orientation was, by the way, able to handle 330 newtons of load, which is more than double of the load bearing capability. Now let's take a look at the hooks with double the wall thickness. Here again, if we also take scatter into consideration, all parts broke on average at roughly the same level of load. Again, around 50% below the reference strength of the lying hook. Even the hooks printed with the emulated big nozzle, where I only increased extrusion width but kept the 0.4mm nozzle, did not perform walls, which is great, because that means if you rarely want to print with larger nozzles, save yourself the hassle and just increase the extrusion width. Sorry, nozzle manufacturers. The results even barely change if we take the weight of the samples into consideration. The strength is basically proportional to the used amount of material, and in this case, the wall thickness. This means that bigger nozzles don't seem to bond layers together better and reinforce the plastic. As I said in the past, I'm working in aerospace, and here it's usually important to use material efficiently, so maximum strength at minimum weight. If you're not concerned with weight, you'll also be able to achieve the same strength of your part at similar wall thicknesses and infill ratios, regardless of the nozzle. Though I guess the interesting point here is in which amount of time you achieve which strength. This is where the advantage of a bigger nozzle comes into play, because they allow you to push more material out in the same amount of time. Disregarding maximum flow rate, cooling issues and keeping speeds the same, a 0.8mm nozzle at double the line width and double the layer height pushes out 4 times as much material in the same amount of time in comparison to a standard 0.4mm nozzle. If we apply this to our tested samples, we can finally see where the bigger nozzles shine and the impression that parts with bigger nozzles are stronger comes from. The strength per time is by factors higher if you print with a larger nozzle and larger layers. In this test, you can even get a similar effect by just upping the extrusion width and layer height on a standard nozzle, though there are limits in the end. I think I was able to nicely show that the additional strength of prints with bigger nozzles result from the additional material that is printed and not any reinforcement in the plastic. I've already made a video in the past about the most efficient way to improve the strength of 3D prints, and that is not the infill ratio, but the wall thickness. If you keep the number of perimeters the same and just use a bigger nozzle, especially the walls will be thicker and therefore the strength is improved significantly. Though these thick walls can be achieved with a big nozzle or a small nozzle by adjusting the number of perimeters. The big advantage of bigger extrusions is if you take the time factor into consideration as well, because with a bigger nozzle you can increase the strength of the part by factors in a similar amount of time. I have shown that you might not always need a larger nozzle for that effect, because if you stay within the capabilities of your system, you can emulate bigger nozzles by just increasing extrusion width and layer height. Going all the way to double the extrusion width and layer height might be a bit too much, but emulating a 0.6mm nozzle with a 0.4mm nozzle and therefore more than doubling your strength per time should be possible without an issue. So consider creating yourself a fast and strong printing profile for your current printer. But what do you think of these results? Leave your thoughts down in the comments. Thank you for watching. I hope you have learned something new today. If you did, then please leave a like and make sure that you're subscribed for future investigations. If you want to support my videos and research, then consider becoming a patron or help me out in other ways. Also check the rest of my video library, because I'm just about to reach 100 videos and there's a ton more for you to watch and enjoy. I hope to see you in the next one. Auf Wiedersehen and goodbye!